I swear it's accurate.
All right, vectors day one. We've actually done vectors already, or something with vectors, whether you realize it or not. Velocity, I think we kind of mentioned that, didn't we? Is a vector. So if I'm going this way, going to the right, what is that? Positive, right? If I'm going to the left, what is it? It's negative. Now, how fast I'm going is a speed, isn't it? All right, so when you hear the word vector, what's the first thing that pops in your head? That's not the first thing. Yeah, you think of Despicable Me, don't you?
Yeah.
I know exactly what you're thinking. And you're thinking that guy doing this crazy thing, and he says, I'm vector because I have direction and magnitude, right? Magnitude and direction. Now the direction we're going to talk about, magnitude we're going to talk about, obviously. You're going to see what those two pieces are. It's not as much as you probably thought it was. All right, so here we go. Before I can get into all that stuff, maybe a couple of just basic terminology. It's a directed line segment. It's kind of like a ray, is what it looks like. It looks like a ray, but it's not technically that. We'll go into it. It has an initial point. So like right here, point A. So this is vector AB. Point A is their initial point. Initial point, and point B is our terminal. So terminal and initial. That would be vector AB. Whereas the other way around is vector BA. So which one's the starting point on vector BA? B ends in A. It's the same thing you guys done in the past. Okay, nothing tricky about that. All right, so let me show you an example of a vector. So I got us one right here. It's PQ. So let's plot that point. -2, 3, and 3, 5. Plot those 2 points. One for P and one for Q. Okay, which point is listed first right here? If I said graph PQ, I'm going to rewrite this real quick. PQ, and this is the vector symbol. Almost like a ray, but not quite. Okay, which point are we starting at? P, and then it goes to Q, whatever that means. So we'll get into directions here in a little bit. This little symbol right here is magnitude. This little double absolute value thing going on, that means magnitude. What is magnitude? We'll get into it more as far as applications. But all I want you to think about it right now is that magnitude is the length of the vector. How far away the points are, basically. So how do you find how far away 2 points are? What was the thing you did in the past? Distance formula, right? Remember the distance formula? Now, the distance formula really is just the Pythagorean theorem. Are you aware of that?
No.
Okay, so that's really all it is. The distance formula is just the Pythagorean theorem. So if you guys are okay with it, just to kind of shorten this up a little bit today, if I go and make this 2 points and just make it a right triangle, now you're just finding the length of the hypotenuse of the right triangle, which is what distance formula is doing. Well, how far is it from here to here? 5. That's 5 units. And you can either count it or you can say, oh, from -2 to 3 is 5 units. Then how far is it from there to there? 2. So if we wanted to determine the length of PQ, it's just 5 squared plus 2 squared, right? And we're going to do the square root of that. Square root of 5 squared plus 2 squared. So what is our magnitude? Root 29. So the magnitude is the length of the vector. The length of the vector. What questions do we have so far? Just going a bunch of terminology right now, a little vocabulary. Yes, sir.
Does the line on top of PQ exist only at the top? Or?
Yes, just the top. Otherwise it'd be ray PQ. So that's how we designate this vector PQ. Okay, anything else? Not anything complicated yet. It's very basic terminology. Okay. Components of a vector. So put like A comma B right here with these little symbols right here on the sides. That's what the component form of a vector is going to look like in this class. There's other ways of doing it. That's what we're going to do as far as notating it. All this means is A is like the X position, if you will. That's horizontal movement, left and right. B is vertical movement, up and down. That's all it's meaning. So a position vector is a specific one. And I'll kind of show you some examples of those. But I will go ahead and use this time to use one more little terminology. If I said vector V, I say I had a V, and it's like we were talking about earlier, that's the symbol you could write for vector V. So it says a position vector is represented by a small case above the letter. Well, that's if you can type it. So if you're just writing it in my hand, that's how we do it. Okay, and the last thing, this should be flipped, by the way. This should say always subtract initial. I'm not sure what's going on there. Initial from terminal. So we'll knock that out. That's not good. It says that in y'all's too, doesn't it?
Yeah.
Okay, I think I have versions out there that are cleaned up, and evidently I didn't use the right one. I apologize. Okay, so that should be from initial from terminal. Basically, find where it stops and subtract off where it began. All right, so if we had if we had this one up here, for instance, okay, what is 3? That's the terminal, right? What's 3 minus negative 2? 5. Okay. So put a little component form up there, 5. And what is the 5, the terminal point for the cube, minus the 3? 2. And what does 5 comma 2 look like to you? This right here, right? Isn't that just a horizontal and vertical movement? It's just describing how far it went right and how far it went up in that case. Yes, ma'am. So if I'm saying terminal minus initial. So if I'm saying it this way, I'd say you're subtracting initial from the terminal points. And that's kind of a flip-flop thing. Basically, just think of it this way. Terminal minus initial. Here, I'll start that. Terminal. That's easier, right? Terminal. I don't want something basic like that to get us. And that's happened before. Terminal minus initial.
But on the board it says initial from terminal.
Right. So take the terminal. Yeah, that's that preposition's kind of throwing things off. A chicken scratch from, sorry. Yeah, let's just forget that. That's confusing. Just have this in your head. I think that's easier, right? Let's just do that. Terminal minus initial. I'll just mark all this out. That confuses us. I don't want that to be confusing. Terminal minus initial. Terminal minus initial. Let's just do that. Everybody good with that? Okay, let's not get caught with the prepositions throwing everything off. All right, English. All right.
You learned that more.
All right, next thing. I talked about magnitude. Right now, our one thought for magnitude is length. Let's also say what direction of the vector. Okay, because we talked about that's 2 pieces of the vector. Okay, here's the part. It's the positive angle, which we can go into that later more, but for right now, it's just the positive angle that it makes with here's the key part, the positive x-axis. The positive x-axis. Okay, so here's a vector. What quadrant is this vector drawn in? Quadrant 1. If I was trying to figure out the horizontal and vertical movement, we could tell it started right here at the origin. We're saying, hey, there's the horizontal movement, and here's our vertical movement, right? There's our right triangle that's created. Well, we've already talked about if we had like vector A comma B, which one represents the horizontal movement? A. So here's the horizontal movement, A. Which one's the vertical movement? B. So you're like, this is the same stuff we've always been doing. Yes, it's exactly right. So how do they get this little equation with the tangent theta equals B over A? Opposite over adjacent. You see where it is? And this theta right here, it's sitting right there, that's the directional angle. Okay, it's the angle that our vector created with the positive x-axis. Like the same things we've been doing here for a long time, right? Okay, so let me go down here to example 2. What's really going to help you is if you draw pictures of these, because they're going to give us some really good visuals. Finally, we're doing some vectors. So we're going to do 2 things. Find the direction, find the magnitude. So I'm going to draw this vector. What quadrant do you think it's in? First quadrant, right? There it is. Drawing quadrant 1. We know that it has lengths of 3 and 4. Right? Okay. Horizontal and vertical. Yeah, you can probably do that in your head, which I hope you can. But if not, it's okay. Remember, the magnitude would be equal to the square root of 3 squared plus 4 squared, which would be 5. So there's our magnitude, it's 5. Okay? How do we find the directional angle? Tan of theta. So I'm going to write I'll write theta this time. Have a calculator ready for me, please. That's not the question. It's okay. Have a calculator ready. All right, so in your calculators, change the mode to degrees. Okay, we're actually in degrees
For all of them?
for all of them. So, say it again.
For all for the vectors?
For all these vectors, it's going to be degrees. Yes,
Will
ma'am.
the test do this all calculated?
The test will have a lot of calculator. I know some of you are like, oh boy. I know. Yeah, there's a lot of calculator. Okay. Did you ever think you would say that before you walked into here? Like, now you don't want calculator. All right. It's just interesting.
Calculator's always the hard part.
Yeah.
For two.
Help me out. Uh-oh.
That equals 36.86.
Did you go second tangent? And we're in degrees, correct?
We could do the inverse.
53.
Yeah, I don't do that.
Okay, 430. So 53 point, 3 decimal places for me? 130. Okay, so got a lot of stuff written up here. Here's our magnitude, right? And there's our direction. Magnitude and direction. Okay, I want to do one more with you, then I'll have you do the other two. There's one little twist I want to make sure you pick up on. So what quadrant is this vector negative 2, 5 in? Quadrant 2. It's over here. And I'm not even going to worry about the negative. I'm just going to label it 2 right here and 5 right there. So just label the links. That's all I'm doing now. Left 2, up 5. Magnitude, let's get that one. Let's use the quicker one. So that'd be square root of
29.
5 squared plus 2 squared, which is square root of 29. All right. Now here's a part we need to be tricky with. We need to be careful with. I'm going to call this angle in here alpha. I'm going to show you why. It's not anything too bad. You'll see why. So if I said tangent of alpha, what does that equal to? 5 or 2. So we're finding a directional angle right now. Is everybody aware what we're doing? Okay, so help me out one more time. On your calculators, 68.19. Okay, I said 199. Okay, so that is not the directional angle though. Why?
Because it's positive.
Okay, the angle we're creating, remember, is the angle created with the positive x. Here's the positive x-axis. It's this angle. That's the angle we need to find for our direction angle. So this one in black is theta. So we're going to take that number and subtract it from 180. Right? So 180 minus, because that's all the way halfway around, would be 180. So theta is equal to, I'll write it out here. Theta is equal to 180 minus the alpha. I'll just write the number, 68 point, whatever we got in our calculator. Right? So what did you guys end up coming up with? 111.801. Degrees. So once again, there is the highlighted directional angle, right there, and magnitude. We good? All right, so let me have you and your partner, y'all do the next two, please. And then we'll check it. Zoom real quick. Okay, so here's the deal. You had your 4 quadrants. Quadrant 1, the directional angle we found was the answer, wasn't it? Quadrant 2, we had to go all the way over, but we had some left over, didn't we? So we had to subtract that from 180. Here's our quadrant 3, the -1, -2 that you guys worked. So we went all the way around, 180 degrees, plus a little bit more, which is the angle you found, using the tangent. And what did you have to do for quadrant 4?
Down all the way to 360 minus 2.
Yes, so you went all the way around, and we couldn't quite cover the distance, the circle all the way around. It's this angle right in here, right, that we need to subtract off, because we didn't get that part accounted for. So 360 minus. Yes, ma'am. So some people like to memorize that. They just go, hey, quadrant 1 same, quadrant 2 subtract 180, quadrant 3 add to 180, Bucket 4, subtracting 360. Some people like that structure, and they just memorize that. Other people just say, I'll just use my reasoning and get it. I don't care whatever one you fall into is fine with me. All right? Okay, let's go here. I need to take one little basic case. It's weird. This is like a very basic statement I'm about to make, we're going to look at, yet it's the one that people miss every year, and it always baffles me. Because if I saw this question on a test, I'd be, give me, won't take that long. Equivalent vectors. Now think about this. They're the same. That's what equivalent means, right? Are vectors that have the same magnitude and direction. That kind of makes sense, doesn't it? Now if I'm thinking about this, I'm like, wait one second. I have to go find the magnitude and direction of this vector and the magnitude and direction of this vector, and it's either the same. Follow that process? But that might be, I can word questions when it does occur, but if you have the points already given to you, which we do right here, vector RS and vector OP, notice they're in different spots, right? Those points are in different spots. We're trying to determine are they equivalent vectors. Instead of going through all this magnitude and direction, let's just find the component forms. So RS, for instance. Might use a highlighter. So RS. Okay, so this is, remember, terminal minus initial. So which one, where does it end on RS? S. So negative, I'm going to write that out this time. -1 minus, what's it going to be? -4. What's the y component going to be? 6 minus 2, a vertical component. Okay, so it looks like we have something like -1 plus 4. So what's that, 3? And what's the last one? 4. So RS component vector would be 3, 4. Okay, so let's look at OP now. OP is probably a little easier, isn't it? You can just look at 3 minus 0 and 4 minus 0, right? So vector OP, what's this component form? 3, 4. Which is the exact same thing as RS. They're the same. They're both 3, 4. So therefore they are what? Equivalent vectors. That's all it is. What, Luke? Okay. So here's the deal. Are they on the same, they look in the same spot on the graph? No, this one's 0, 0 to 3, 4, and that one's -4, 2 to -1, 6. But they're going to have the same direction and the same what? Magnitude. So they're going to kind of look, what do you think how they're going to look?
I think parallel lines.
Are they going to kind of like parallel lines a little bit? They're not lines, they're vectors, but you can see they're kind of floating out there. All right, so just have a visual in your head. All right, so that's a basic one. Here's what I want to finish off with on this part of our lesson. Then I'm going to show you kind of some applications with it. Operations. Operations are exactly what you hope they would be. Like you're thinking, oh great, like new rules. No, it's very simple and straightforward. So if I said to U, here's what I want to do. First thing I want to do is draw a picture of vector U. So vector U would be right 2, up 3. There's vector U. I'll go ahead and label it right here to the right. This is not 2U, this is just the vector 2, 3. Good so far? Okay, so 2U, what do you hope it means? Double it, okay, I see. So that would mean 2 times 2, 3 in component form. And you guys are right, just distribute the 2 in. And scalar multiple. So 4, 6. So if I go on our graph, need 2 more units for the 4, 3 more for that to get the 6. So 4, 6. I'm going to start from the origin still. On this one I am. I'm going to draw that red one now. This represents 2 times vector U. Essentially, what did we do to our vector? We just doubled it. We just made it twice as long. Right? Twice as long. Magnitude double. Did the direction change? No. didn't change at all, just the magnitude. All right, negative W. I want to go the opposite this time. What do you think negative W's vector is going to be? 2, -1, I agree. 2, -1. So let's see what that looks like when we graph it. So let's graph W first. -2, 1. There's W. Put the point that time. Usually I don't put the point. I got it. -2, 1. Should have done that in red. Then negative W, which I'm going to highlight in red real quick to kind of help with the color coordinating here. Where's that going to be? Right 2, down 1. There's negative W. Which I didn't draw very well. But literally, what did it do to that W? Just make it go the opposite direction. Have we done that before? Which way am I heading right now? Going right, which would be a positive what? Velocity, right? I'm going the same speed this way. But what is my velocity now? Negative. That's literally going the opposite direction. See what I'm saying? It's the same magnitude and direction. I'm sorry, same magnitude rather, but the direction is the opposite one. Opposite direction. That good? Okay. Any questions? Here's where it gets real now. Okay. U plus W. This is a big idea for us right now. Find that real quick. Find U plus W. What'd y'all get? 0,4. I completely agree. 0,4. All right? I'm going to go down here and use this space. I'm going to open up another space. You can fit yours all right here, but I just want to make sure we can see it really well. Is everybody good with 0,4? All right, here we go. So we went, here's U, and here's W. So we added the 2 and the -2 to get the 0, and we added the 3 and the 1 to get the 4. So add the horizontal components, add the vertical components. Very simple. All right. Here's the main idea. We're going to draw that situation really quick. Okay, what was vector U? Help me out. I don't know what it is. 2, 3? Okay. So 2, 3. Looks like that. And this is vector U, isn't it? It's U3. I got vector U labeled. Okay, we added W to it, isn't that right? -2, 1, is that what it was? -2, 1. All right, watch how I do this. If we're adding vectors, our initial point for U is right here at the origin. Our terminal is right there, correct? So we're going to add a vector to it. Our new vector is going to start right here where this other one ended. So we're not going to go back to the origin. We're going to start right where this one ended. You follow it? This is when we're adding vectors. So from here, we're going to graph it. Was it W? Is that what it's called? It was left 2. So 1, 2, up how many? 1. There is vector W in this spot. So we use the terminal point from our first vector as our initial point for our second vector. Really all I'm saying is just draw your new vector where your first vector stopped. Am I saying that clearly enough? Okay. Does everybody see this? Here's what I want you to do. You started, I'll go on black here. You started right here at the origin, right? And when we added W to it, where did it completely end? At this spot, right? You'll see it? Connect here to here. Draw an arrow. Okay, so we did this connection. I'm going to bold this out really well here. That is a vector we just made, isn't it? It's the vector U plus W. What can you tell me about that vector? What's its component form? 0, 4. We moved left and right, none, and went straight up 4 units. 0, 4. That's how we add vectors. we're going to be adding vectors a lot. That's the point I'm trying to make. Okay? Write this below it as well. It's also very common. We'll call that vector R, which represents resultant vector. That's what I'm talking about when I say resultant vector. Any questions on that part? Here's what I want you to do. You have, don't you have some space at the bottom down here? All right. Yeah, bunch of space. So complete this one, you and your partner, the negative 2u minus 3v. Get the computation all set up. And then I want you to go down here and see if you can draw the situation that occurs. All right, let's break off and we'll come back together. All right, so here's your resultant vector, 14.3. Saw that in other papers just walking around. That was good. The picture is the hard part, right? So look, negative 2u. I saw some of you actually label it that. That's at negative 4, negative 6. And then what did we do with this negative 3v? We did not start it at the origin. We started at where that one ended, right? Where negative 2u ended. And then 18 to the right, 9 up. That's the negative 3v. This R resultant vector, what's that one? Which one is that up here? 14 comma 3. Okay, 14 comma 3. I'm going to tell you why that's occurring. In fact, I'm going to go and do that right now. I want you to have a global view of what's about to happen. Say you have an airplane. Okay, and it's going that direction. Right? What's being applied to that airplane up in the air? What do they have to account for? Wind. Okay, so say the wind is it's hitting this airplane, it's going to push it that way. Well, this is blue part that I'm writing right now. What do you think that represents? That's the actual path the airplane's going to be on. Okay, so this first vector we drew, that's like our normal, that's the plate, okay, we're aiming that direction. The wind's hitting that airplane, that's the blue one's the actual path it's taking. That's the kind of problems we're going to be doing. Okay, think about this. Like if you're, I don't know if maybe you've been driving before, or you've seen your parents driving, if you're out somewhere where the wind's really blowing, and they have the steering wheel, they're not just like this. You're noticing how their hands tip, the steering wheel actually looks turned a little bit. Why? Car's hitting it. They're having that count for that wind. Okay, so that's a very applicable situation. I see them all the time. Okay, so here's what I want to do. This is where we're going to stop. We're going to go just these first couple, and then you'll be set up for the rest of the way. All right, let's connect. Like we talked about this magnitude and direction. What is it actually referring to? Well, here's what happens. We have this picture we've been working with the whole time. We have a vector v. Obviously, that has the magnitude indicated, the length. Cosine of theta, what would that be if this is our triangle? X over the magnitude of v. Okay, what would sine of theta equal? Y over the magnitude of v. Okay, so using algebra, if cosine of theta is equal to x over the magnitude of v, what does x equal? Well, just using this part right here. How would you change that? Yeah, multiply the magnitude over to the other side of the equation. So x is just the magnitude of our vector, vector v, times cosine of theta. Therefore, y is the same thing, except it's the magnitude times sine of theta. So notice that x has always been cosine in this class. and y has always been sine, like with the unit circle. So if we were going to write this as our component form, which remember means left and right movement for the x component, the first component, and vertical movement for the second component, it would look like this. Magnitude times cosine of theta, comma, magnitude times sine of theta. And you're going to use that over and over and over again. That's the component form for our problems we're going to be working with. Magnitude times cosine of theta, magnitude times sine of theta. So for instance, if I gave you this problem right here, okay, find the component form of the vector shown. So we have 23 and 40, right? What does the 23 represent? The magnitude of our vector. 40 degrees is our directional angle. Okay, so we're simply going to say, hey, for this vector, I'm going to call it V. Let's just call it vector V. So for vector V, that would be equal to, well, we already know the magnitude, 23, times what? Cosine 40. And then 23 times sine of 40. Go to calculators and punch those in, please. 23 cosine 40, 23 sine 40. Okay, what did y'all get for the horizontal component? 17.619. Okay, what about the vertical? 784. Is everybody getting the same answers? Sweet. All right, so that would be, that's the component form for our vector. Okay, so if 23 is the magnitude, what is this 17.619? What does that represent? The x, how far we went to the right, right? What's this 17.784? How far up? Okay, it's our triangle. Okay, so you and your partner, real fast, do this one right here. We're talking about the directional angle is 225 and the magnitude is 25. Here's what I wanted to clarify. So you got negative 17.678, negative 17.678. Why does that make sense? Yeah. What quadrant are we in? 3. What angle is 225 degrees? That's in what quadrant? It's in quadrant 3, right? 225, so that's where tangent is positive. Yes, quadrant 3. So that's why we have a left movement and a down movement. You follow? All right, so here's what I want to finish. Last one of the day. Done good. Example 6. I want to give one little application so you can see how it works. So we're going to throw it into, it looks like a velocity problem. Find the component form of our airplane velocity vector traveling 200 miles per hour. What's the 200 miles per hour represent, you think? So velocity, that would be, was that magnitude or direction? That's the magnitude. Okay, so let me talk about magnitude. Up to this point, it's just been the length of a vector. And what it represents in application problems is like a speed, or how fast something's going, or a force, like how hard I'm pushing something or pulling something. That's what the magnitude is going to represent. Okay, those are the types of problems we're going to be working with. Okay, and then directional angle, I think that kind of speaks for itself. Which way are we facing? So that makes you kind of think like bearing problems in the past. And you can already look, if you look ahead, you can see there's a little bit of a bearing aspect to it. Okay? She means yes. All right, so on this part right here, component form of a velocity vector, I'm going to call it V. Okay? What would it be? 200. Now, can I go ahead of myself here? I'm going to draw the picture for this one over here. It says, in a northwesterly direction, exactly halfway between north and west. There's our vector right there. So what is this angle? Well, it's right in the middle of the 45. So what's the angle, the 45 angle? 135. It's that one right there, right? So it's 135 degrees. So that'd be 200 what? Cosine of 135. comma, 200 sine 135. Sorry, it's kind of squeezed in. Yes, ma'am. Okay, so since it's in a northwestern direction, that would be right over here between north and west. Theta is, remember, our directional angle is from the positive x-axis to that spot. We've used the directional angle. This is the first time we've had one, I believe, in this series. No, the 225, the same thing. Remember the point you before? Negative 17 point. 225 is a quadrant 3. It's that directional angle. Yeah, you're right. All right, hey, what'd y'all get for this one right here?
Negative 141.42.
And positive 141.42.
Is that what we got?
Yeah.
So negative 141 point, what was it again, sorry?
421.
421. And positive 141, 1421. No, they're not always the same. You guys have already seen that. Okay, so the last one I want you to do is, we're going to stop here on this one and see if you can get that wind problem right there. All right? Okay, so negative 10, comma, negative 17.321. Here's your assignment. Here's your assignment. It's 2 parts. Okay, so day one homework is, you'll see it on Canvas. You can go and find it. You do this on your own piece of paper. Many of these are very quick. Here's, hey, are they equivalent vectors? Yes or no? You can maybe even do that in your head, to be honest, some of those. Then you go down here. Write the vector v in component form. We just did that, didn't we? Magnitude times cosine, magnitude times sine. And so we're going through all these, and then we start seeing, hey, find the velocity of the plane as a vector. And all these are fairly simple, a little bit of bearing, but it's the same thing that you guys were doing. As you get further, look, now we have the u plus v stuff, which is what we did at the end of day one stuff, right? But now you're going to do applications associated with those, which we have not done yet. That'll be the next video that you guys are going to need to watch for day 2. Okay, so you do as many as you can. You're going to see, like, when you get to 31 and on, today, that's an issue. But after you've seen day 2's piece, which for those of you who are in class right now, that's on Friday, you'll be able to do all of it. Okay, so the second part of this lesson. So we stopped at 6. Make sure I make this clear. Okay, we stopped at 6. That requires the rest of these, the packet I gave you, 7 on. All right, and that'll be the video for day 2. For those of you that are in class on Thursday, you don't have to worry about that because that'll be the lesson on Monday when we get back from the break. All right, so I'll cover that part of it. Okay, so this is, I just want to make sure people in here, if I have to leave it at that. So those of you that are in class, next class, or Thursday rather, that'll cover all of these problems until number 31-ish. Then you're going to have to kind of wait for the second part later on. Those of you in the video world, have a good one.